So hi everybody, welcome to Outstanding Young Chemist Award 2021 Winner Showcase webinar. I'm Yvonne, I'm currently an assistant professor at Xiamen University, Malaysia, and I'm here today as the moderator, MC, and I'm basically hosting the event today. We have with us two very important people who are winners of our Outstanding Young Chemist Award, both for the academic category as well as for the industry category. We'd like to welcome them in order shortly. But to give you an idea of what we'll be covering today, it's going to start off as follows, starting off with a brief introduction, which I'll be giving the microphone over to Dr. Juan for a welcome speech, then over to Dr. Ng as the first speaker. The Q&A would follow right after his speech. We'll then followed by the second speaker, Q&A, and a closing remark before the group photo. So if you're not ready for a photography session, please get ready by 4:30. A little bit about housekeeping rules. Please keep your cameras and microphones off while the speakers and moderators are presenting or hosting. Only turn them on if you have questions to ask during the Q&A session, as well as during the photo session. Please use the chat box for the Q&A session. If you look over on the top of the bar, there is a chat. And if you click on that, you will get to enter your questions there. You're allowed to type in questions at any time during the presentation. However, if you choose to unmute yourself, that will be during the Q&A session. There's a disclaimer today that is, this webinar will be recorded and kept for documentation purposes. Right, I would now like to pass over the floor to Associate Professor, Chemist Dr. Juan Ching, the Chairman of Malaysian Young Chemist Network. He's also the Honorary Assistant Secretary of Institute Kimia Malaysia. Dr. Juan, the floor is yours. Over to you for a welcoming speech.
Thank you, MC, Dr. Yvonne, Choo. She also the co-opted member of IKM, the council member of IKM. So I'm Juan, I'm the Assistant Honorary Secretary of IKM and also the Chairman of Malaysian Young Chemist Network. Currently also the Associate Professor at University of Malaya. So I would like to first welcome all the participants here, especially our two guests of honor. One is Associate Professor Dr. Ng and also Khalisanni. So they are the winner for the Outstanding Young Chemist Award, which we have started last year, 2020. So we still have this opening, and this will be a yearly award. So those are qualified, please apply for this Outstanding Young Chemist Award. So I briefly tell you about the Malaysian Young Chemist Network, MYCN. It started in 2018, okay? So they inspired by the president, and I'm the founder for this MYCN, because I think that we, as a young chemist here, have more important role to play in that sense to make the advancement of chemistry, so that we can contribute to the society. There are many challenges that faces currently. For example, the climate change. So that's why we also have this SDG goal 2030, and chemist is play an important role to fulfill this SDG 2030. Okay, one of the issue, of course, I mentioned just now, climate change, water securities, food securities, energy. There are a lot of pressure, and also especially during these 2 years upcoming to this 3 years pandemic of COVID-19. This is the challenges that we have to face. As a young chemist, we again need to bring up this one, okay, to take up this challenge. They are first, this Outstanding Young Chemist Awards started 2018 actually, when we formed the Outstanding MYCN. However, during these times there are challenges. Okay, after 60 years of IKM, Institute Kimia Malaysia establishments, so this is our first time we acknowledge and recognize our young chemists. So it's a journey. It took 2 years together with the committee member of MYCN and also and this, of course, this outstanding young chemist award led by Dr. Pang Sok Wai. So and their team, okay, together, right, in MYCN committee, we make this reality. There are a lot of challenges. To be frank with you, we take 2 years, okay. Even, okay, Dr. and Dr. Khalisanni, even the medal that you received last year, I nearly threw my chair because previously they have promised us, I say it's a plaque, but they do not agree. Okay, they say that outstanding academic should not receive anything, just a cert. So I disagree with that. Okay, I really throw my chair. So really, you have to keep the medal, Dr. and Dr. Khalisanni, keep the medal and appreciate the medal. Okay, we fight very hard to establish this outstanding young chemist. This is not to actually, it's a lot of work have been done by a young chemist. This is one of the recognitions so that we can work harder, right, to achieve better in our life and also for the betterment of our community. Okay, so that's why we are giving out this award as an encouragement to our fellow young chemists. So again, I would like to encourage, okay, those are qualified to apply. Whether you get it or not is another agenda, okay? Not everyone will be the winner of this award, but at least you try. Just at least give a platform to try, okay? To become a better, okay? Because we do recognize you, okay? In IKM Institute Kimia Malaysia as outstanding chemist award, okay? So it is a bit of IKM, a bit of MYCN. And currently we have around 100 members in MYCN. So the number is very encouraging. It's increasing every month. So those are interested, so you can fill up the form and join us MYCN, Malaysia Young Chemist Network. Okay. And for IKM, so this year, 2 months ago, we have reached 5,000 membership. Okay, so this milestone for IKM, the chemist is no longer a small body. We are a professional body, very strong professional body in Malaysia. So hopefully we can contribute to the society. So I think I pass back to our MC, Yvonne Choo. Thank you.
Thank you very much, Dr. Juan, for opening up today's webinar with a welcome speech. We'll now like to move on to our first speaker today. Give me a sec. So our first speaker today is Associate Professor Chemist Dr. Ng Eng Po, who happens to be my lecturer when I was an undergraduate. So our first speaker today is the winner of the academic category. So allow me to start off by telling you more about him and his background. Associate Professor Chemist Dr. Ng Eng Po received his bachelor's degree, first class honors, in industrial chemistry and master's in chemistry from UTM, University Technology Malaysia. He then obtained his PhD degree from University of Mulhouse, Alsace, France, under the supervision of Professor Dr. Svetlana Mintova. After that, he pursued his postdoctoral research in the University of Caen, France, and he was later appointed as the senior lecturer at University Science Malaysia. In 2016, he has been appointed as the associate professor of physical chemistry at University Science Malaysia. Sorry. He's currently the Deputy Dean of Research, Innovation, Industry, and Community Engagement at the School of Chemical Sciences, USM. Dr. Ng's main research areas are synthesis and application of nanopore silica-based materials for advanced applications, particularly in nanotechnology, catalysis, energy, and environment. Currently, he has published 1 book, 6 book chapters, and more than 140 index journals, with nearly 90% of them are Q1 and Q2. His current H index is 35 and more than 4,200 citations are recorded up till now. Dr. Ng is also active in innovation. So far, he has 6 innovation awards, 12 copyrights, and 1 patent granted from his research work. In addition to that, Dr. Ng has received many prestigious awards at national and international levels. So that includes one of his research work has been selected as one of the top 10 breakthroughs of the year by Science Journal. In the same year, he was recipient of National Academic Award in Journal Publication category. He also received several academic awards and recognitions from international bodies like Outstanding Science Award from India, Leading Scientist of the World from England, World-Class Professor from Indonesia, Visiting Young Scientist of Lindau Nobel Laureate Meeting from Germany, and recently the 2021 IKM Outstanding Young Chemist Award. Right, without further ado, let us give a warm welcome to Associate Professor Chemist Dr. Ng Po, who will be delivering a title and a topic entitled Green Synthesis Strategies and Advances in Nanosized Zeolites. Dr. Ng will now pass you the floor. You can start any minute from now. Thank you.
Okay, thank you very much, Dr. Yvonne Choo. Can you see my slide?
Yes, Dr. Ng, we can see it.
Okay.
Yeah, everything's all right now.
Okay, so first of all, I would like to thank Malaysian Young Chemist Network, Institute Kimia Malaysia, for giving me this great opportunity to present my research work. Today, I'm going to present my work entitled Green Synthesis Strategies and Advances in Nanosized Zeolite. So as an introduction, what are zeolites? So zeolites are crystalline microporous materials with defined micropores ranging from 0.3 to 2 nanometers. Zeolites have a high surface area ranging from 300 to 1,000 meters square per gram. When we measure the length of 1 gram of zeolite, it has a total pore length of 600 million kilometers, which is the distance, 4 times the distance from the sun to the earth. So that means this porous material, it has a very what you call high surface area. And zeolites can be used in many applications, particularly in catalysis, gas, and molecular separation ion exchange processes, because they have this tunable chemical composition. They are chemically, thermally, and mechanically stable. In addition, zeolites are non-toxic and also environmentally friendly. And most importantly, they are recoverable and reusable. So recently, many attention has been paid on colloidal nanoscale zeolites because decreasing crystal dimension can reduce the diffusion length and further reduce the mass transport limitations. In addition, subdivision of materials into fine particles will lead to immense external surface area and further affects the magnetic, supramolecular, optical, electrical, and catalytic properties. While more than 260 types of zeolite are known today, there are 24 types of aluminosilicates, pure silicates, and aluminophosphate zeolite that can be synthesized in nanometer scale. Conventional zeolites, which have a crystal size larger than 1 micrometer or 1,000 nanometer, are normally used in catalysis, adsorption, and ion exchange processes. And these conventional zeolites normally cannot be used or very seldomly used in nanotechnology application due to size limitation. On the other hand, nanoscale zeolites can be used in many emerging applications, like in the nanotechnology and nanoscience application, because these zeolite nanocrystal with the particle size 10 to 1000 nanometer can be easily dispersed and stabilized in colloidal form in water. And this colloidal system is very stable, and the zeolite nanocrystal will not settle down for example, more than 6 months. Okay, and then this colloidal system of zeolite enable the zeolite crystals to be used in many applications, for example, in atomic energy production, food, paper, drug delivery, ceramics, paint, pigments, electronic recording material, lubricant, and detergent. Conventional zeolites are synthesized from dense gel, which results in the multimodal particle size distribution solid product. And normally the zeolites are sedimented in the mother liquid due to large crystal size. On the other hand, nano-sized zeolites are synthesized from clear solution using colloidal sources or molecular precursor of silica, alumina, sodium oxide, water, and also organic template. And this organic template is served as an organic additive to direct the zeolite structure formation, to control crystal size, and to prevent crystal agglomeration. Usually for the synthesis of nanozeolite, we use a low synthesis temperature, for example, from room temperature to 100 degrees Celsius, in order to control nucleation over crystal growth. And the use of this system leads to the formation of a nanoscale zeolite with more monomodal particle size distribution and colloidal stable solution. However, using this method, the crystalline yield normally is low, which is less than 10% of based on the total mass, and this is difficult to scale up. And also this is because of the use of a plenty amount of expensive and harmful organic templates. In order to solve this environmental and production cost problem, several strategies have been proposed. For example, the template-free method. By using this method, no organic template is used. Therefore, the synthesis cost will be lower, and it makes the synthesis to be more eco-friendly because we don't use expensive and harmful organic template. So it makes a scale-up process in industry for the synthesis of nanoscale zeolite to be possible. So so far in our laboratory, we have synthesized about 10 types of zeolite nanocrystals by using this template-free method. In addition, we are also interested on using agricultural waste as a silica source to synthesize nanoscale zeolite. For example, in this example, we use rice husk as a silica ash to crystallize zeolite L nanocrystals. And this method is considered as a turning stone into gold approach because we can use this agricultural waste to convert it into a more valuable materials. So far, 6 types of nano-sized zeolite have been synthesized by using this rice husk silica. In addition, for agricultural waste, bamboo leaf is also another biomass that is underutilized. Therefore, we have made the first attempt to use a bamboo leaf to synthesize a nanoscale zeolite. As you can see here, this is a dry bamboo leaf. So first we treat it with acid, and then followed by a combustion at 600 degrees Celsius. And this will give us a very pure amorphous silica, which is 99.4% of purity. Where we use this silica to synthesize nano-sized zeolite white, which is a very industrial demanding zeolite. As you can see here, these are the zeolite nanocrystals SEM image, and this is the TEM image. the average size of the zeolite zeolite Y is about 150 nanometers, and it has a high specific BET surface area. And we also use these zeolite nanocrystals as a absorbent for dye removal, where it shows an excellent absorption capacity, which is 4 to 5 times higher than a common absorbent. In addition, the synthesis of LTJ type zeolite, this is a very difficult synthesized zeolite because of low reproducibility. By using Rhyhus ash as a silica source and potassium hydroxide as inorganic structure directing agent, we managed to synthesize a LTJ type zeolite in nano-size form. And more importantly, this zeolite is in a very pure form. Okay, so this is what you call the XRD data, proof that this material is very pure. And also another characteristic of this system is the zeolite system is colloidally stable. So this zeolite is active in catalyzing noble reaction, giving 88% of conversion within 2 hours of reaction. Cesium aluminosilicate zeolite is very rare in the nature. So the first paper reporting on the synthesis of cesium zeolite was 40 years ago, which is 1980s. So within these 40 years, there are only 3 papers reporting on this cesium zeolite, because this zeolite normally it requires extremely high temperature and high pressure to crystallize. However, recently we managed to synthesize cesium zeolite at a very mild condition, which is 180 degrees Celsius, and within 24 hours using cesium hydroxide as an inorganic structure directing agent. And this system, we did not use any organic template, and they are very colloidally stable. So we can use this material for many applications. For example, here I show one example to use this material as a superactive catalyst in base catalyzed reaction, such as in cyanoalkylation. And recently, we also use organo template free system to isolate metastable EMT type zeolite by controlling over the very early stage of crystallization. So this EMT type zeolite is very important in petrochemical industry, because it is an excellent catalyst for fluid catalytic cracking. And by using this system, template-free system, we managed to synthesize the smallest known zeolite, which is less than 15 nanometer, and also the most open pore zeolite. And by using microwave irradiation, we also managed to reduce the synthesis time from 10 days, 100 degrees Celsius. If you use a normal oven, we managed to shorten it to 2 minutes at room temperature, 30 degrees Celsius. So this work has been published in Science in 2012, and also in Chemistry of Materials in 2012 as well. In addition, we also use other strategies to synthesize nanoscale zeolite. For example, multi-cycle synthesis method. So this method is based on the reuse of a zeolite synthesis waste solution after necessary chemical compensation, and then we use it for subsequent cycles of zeolite synthesis. So that means we don't discard any zeolite waste solution into the environment, but instead we reuse this solution for the subsequent cycles of zeolite synthesis. And here I show you an example of Alpo 18 nano zeolite synthesis, where I synthesize using 3 cycles. And you can see here the particle size, the surface area, and the porosity, and also the chemical compositions are quite identical for these 3 cycles. Furthermore, we can see from here, this is a conventional synthesis method. This is a multi-cycle synthesis method. We can see that the consumption of multi-cycle synthesis method consume much lower chemicals. So this will make the synthesis cost to be lower, and it makes the synthesis scaling up process to be possible in industry, and it is more eco-friendly. And this similar system we also applied in cesium ABW zeolite, and it has been published very recently in 2020. Furthermore, we also use zeolite waste solution to synthesize many types of zeolite nanocrystals. For example, Alpo 5, Sapo 5, Alpo 18, Sapo 18. And this strategy shows that this strategy, it works to synthesize many types of zeolite particles using this hazardous chemical waste. And we use these 4 types of nanomaterials for thin film deposition. And here you can see this is the appearance of the thin film, and this is the SEM images of thin film. So we use this for sensing application. In addition, we also use ionic liquid as a green solvent and template for synthesizing zeolite nanoparticles. For this method, we call it as ionothermal synthesis. And this approach can be conducted under ambient pressure because ionic liquid has low vapor pressure and low toxicity. And usually the synthesis yield will be high due to the unique properties of ionic liquid. Furthermore, the non-reacted ionic liquid after the synthesis can be reused. Okay. So now I would like to show you the applications of nanozeolites. So first, we can use it for making a thin film. So as I mentioned to you just now, these are the 4 types of zeolite thin film synthesized using what we call the aluminosilicate, aluminum phosphate, and also silico aluminum phosphate. So we can prepare this zeolite thin film using a spin coating approach, where first the colloidal solution and ethanol was deposited on the what we call silicon wafer, and then we allow it to evaporate under fast spinning. So this is the appearance of a silicon wafer. Okay, and this is the data of the absorption of water in Alpo 18 thin film. So this is one of the data, okay, of this thin film. Then the second application that we have made is use these zeolite nanocrystals in holography application. So holography normally we apply in our banknote. Okay, so by using these 40 nanometer zeolite nanoparticles, we managed to prepare smooth and very thin photopolymer layer. Okay, so the thickness is about 6 to 10 nanometers of the layer. And then we also found that by using the concentration of zeolite nanocrystal as low as 2.58%, we managed to get an optimal holographic effect. Okay, so this is very important for preparing this holography. And next, we also use zeolite nanocrystal as an eco-friendly antioxidant. So in this work, we oxidize the oil using pure oil, pure-based oil, and also the oil containing this nanozeolite as antioxidant. And then we compare the oxidation process using NMR FTIR, total acid number analysis, colorimetry, 2D GCGC for monitoring purpose. So as you can see here, this is the oxidation from 0 hour to 10 hours without any zeolite. You can see the oil turns darker faster than the oil oxidized with nanozeolite. And here you can see with without zeolite, we can see a lot of black particles what we call stick on the wall of the round bottom flask. And here we also compare the antioxidation performance between a traditional antioxidant and nanozeolite, and we analyze it with NMR. And you can see this is the virgin oil after 8 days. It contains a very high what you call carboxylic acid and aldehyde. And for the 8 days, is slightly smaller, and the lowest intensity is shown by nanozeolite, the oil oxidized with nanozeolite. So this means that the nanozeolite has a better performance in halting oil oxidation than traditional antioxidant. Furthermore, we are also interested in toxicology research of nanozeolite because this is important to check whether nanozeolite is harmful to human health, human body or not before we can use it in biomedical research, such as in drug delivery agent, blood coagulation, MRI contrast agent, biomedical sensing application. So this work we have collaborated with Stanford University and University of Kong, and we have studied several types of zeolite nanocrystals, and the result shows that the zeolite nanocrystals, they are not harmful to our human body. So that means we can use it for biomedical application in the future. Furthermore, zeolite can also be used as a micro extractor. So that means zeolite can be used to selectively remove some harmful or targeted molecules from the sample. For example, here, this ochratoxin A. So this is a very toxic compound produced by fungi in food. So you can see 5 microgram per kilogram. So this is what I call the toxicity of this OTA. So by using this LTL zeolite, we can selectively remove this OTA, and this what we call the extraction performance of zeolite LTL is comparable than as an expensive molecular imprinting polymer, or even much better than other commercial adsorbent. Okay, so that means this zeolite is cheap, and the second point is it has a very high selectivity in this extraction, and also high recovery. And lastly, we also use this zeolite as a high performance catalyst. For example, here I show some examples of the nanozeolites in the selected organic synthesis reaction. For example, this potassium LTJ in novel condensation in the synthesis of jasmine aldehyde, giving 88% of U. Iron impregnate on potassium LTL zeolite in oxidation of phenol, giving 72% yield of hydroquinone. Cesium ABW in Henry reaction of benzaldehyde, giving 1 phenyl 2 nitropropene in very high yield, 82.6%. Nickel oxide dope on zeolite Y nanocrystals in deoxygenation of triolane, giving diesel 94.6%. Decomposition of dye using silver impregnate on zeolite X nanocrystals, where the decomposition up to 100% decolorization occurred under room temperature and 8 minutes. And also outdoor condensation, potassium F nanozeolite in synthesizing jasmine aldehyde, 71.6% yield, cyanoethylation, methanol, potassium MER type zeolite, giving 3-methoxypropyl nitrile, cesium polyoxide in Perkin condensation, giving cinnamic acid 90.2%. And lastly, mesoporous cesium polyoxide in Khalisanni condensation, giving chalcone in 82.2% yield. Okay, so as a conclusion for future prospect, zeolite chemistry is complex, and it makes the preparation of nanozeolite intricately challenging. However, recent progress brings a bright future to these unique and versatile nanomaterials, where clear strategies to optimize their synthesis, make them more greener, cost-effective, and practical to industrial production. Furthermore, useful strategies for functionalizing zeolite nanoparticles open more possibilities of using these nanomaterials in many areas. And lastly, clear evidence on human safety allowed them in emerging application used in future, including in chemical sensing, biological analysis, drug delivery, medical imaging, and other biomedical application. So this is one of a very good example for the oil purification using zeolite nanocrystals. So this is before the oil was very dark, and after purified, it becomes very clear using these zeolite nanocrystals. So for acknowledgement, first of all, I would like to thank School of Chemical Sciences for giving me this platform to do research. And next, I would like to thank Professor Dr. Svetlana Mintova, Professor Dr. Halimaton Hamdan, my former supervisor, my collaborators, my PhD and postdoc, my master students, and all of you who attend this seminar. So that's all. Thank you for your attention.
Thank you very much, Associate Professor Dr. Ng Eng Po, for the wonderful talk about nano-sized zeolites. It's really interesting to see how these amazing tiny cages could be involved in, like, for example, holographic as well as high performance catalysts. Right, we do have some questions in the chat box. So if you head over to the chat box, there are a list of questions. One of them, actually 3 of them from Dr. New. Dr. New have a few questions covering both the scientific and general areas. So her first question is, regarding the nanozeolites as antioxidants, how long can this zeolite nanoadditive last without getting oxidized?
How long can this zeolite nanoadditive last? Okay, so according to what we discovered, this zeolite, it has this antioxidation properties, and these properties are actually the way of zeolite inhibit oxidation. The mechanism is different from the mechanism that we found from traditional antioxidant. So the traditional antioxidant is a phenolic compound. So it can what we call capture this what we call the radical. Whereas for this zeolite, maybe I can show you. Okay. Can you see this slide?
Yes, we can see it.
Okay, so so this is how the zeolite what I call inhibit oil oxidation, where the potassium this is what I call the cation of the zeolite at the extra framework. It can stabilize the hydroperoxide group. So by stabilizing this hydroperoxide group, so it will inhibit the breaking of this bond. So it will what you call, it will reduce the formation of OH radical, and this will slow down the oil oxidation. Okay, so basically the antioxidation mechanism from this zeolite and traditional antioxidant, they are totally different. Okay, so this is hopefully I can answer your question.
Right. I will take one more question, and then the other question, Dr. Ng, you can reply through the chat box. So the second question that Dr. Niu had for you is, can you share your experience on publishing in science? Do you find the publication process more challenging or demanding as compared to any other journals?
Okay, yeah, this is quite a very interesting topic. Okay, so how do you find the party? Okay, so the first thing, if you have a very interesting result, the first thing you need to do is you should try to find a famous collaborator. Okay, this is very important. So if let's say you are from Malaysia, if you want to what we call to submit your paper to Nature, to Science, Nature materials, the first thing the editor they will what we call they will see about what I call the authors. If the authors they are from what I call some of them are from a very famous group, so the editor they will consider. If they see let's say the authors all are from Malaysia, for example, so the chances to get through this the editor step will be very low, the chance. Okay, so this is the first step, and then the second step is about what you call the reviewing process. So for the reviewing process, basically we have about two to three reviewers only. Okay, so 2 to 3 reviewers, and normally the what you call the reviewing process, it will take about 6 months. Sometimes some people they can go up to 1 year for the reviewing process. 1 year, for example, like Nature nanotechnology. They took about 1 year for the reviewing process, and then after they send back the what you call the report, then we need to do like what I call the revision for another 6 months, and then send them back again for the revision another 1 year. So total the revision process will be 2.5 years. So this is the experience of my friend. So 2.5 years to get one paper published in Nature Nanotechnology. So for my case, I was quite lucky during that time. About 4 months. Okay, about 4 months. Then one reviewer reject, another two accept. So that's why the what you call the editor decide to accept this paper. So basically the comment is very short. It's very short. It's not like the comment that we have in the normal journals. So the comment is very short, but then it's very what we call specific. So this is what I call the quality of the comment given by the this reviewer. Okay, so and also if you have this very interesting result, so try to what I call to find the collaborator, very famous collaborator, and then you can share with them about your result, and then to ask whether they are interested to publish with you in this journal. Then I think they are very happy to collaborate. Okay.
Great. Thank you very much, Dr. Ng, for answering some of the questions. Of course, there are still some more questions rolling in, but due to time constraints, Dr. Ng, you could still reply them through the chat box. Great. Thank you very much once again. I would now like to move on to our second speaker. Let me share screen for now. Right. So our second speaker today is from the industry category. Technologist chemist Dr. Khalisanni bin Khalid is the IKM Outstanding Young Chemist Award 2021 winner for the industry category. So allow me to read a little bit about his introduction before we invite him. But before that, may I know if Dr. Khalisanni is on the line? Yeah. All right, hi. Hi. Okay, so Dr. Khalisanni pursued his BSc. He graduated with a BSc honors in applied chemistry from University Technology Mara. He then moved on to do his master's under the National Science Fellowship, Masters of Science in Physical Environmental Sciences in 2011 in University of Malaya. He also did his PhD majoring in Physical Organic Chemistry and Nanotechnology in University Malaya. He is currently the Senior Research Officer of the Biotechnology and Nanotechnology Research Center at Malaysian Agricultural Research and Development Institute, Mardi, Serdang. So Dr. Khalisanni has 10 years of diverse research experience in many areas, which includes coding, kinetics and mechanism, natural products, food chemistry, colloids and surface chemistry, nanotechnology, renewable energy, fermentation, analytical and environmental chemistry. In 2012, he was approached by a local company, Qzan Sendran Berhad, to lead research in the area of flavor and fragrance and consulted the Para Agricultural Development Corporation for distillation processes of essential oil. In 2017, he collaborated with KPG Resources for the research of nanofertilizers. Not only that, he continues to devote his time in many different areas in learning, discovering, and enhancing the knowledge and technology in research, and has received many recognition for his excellence. So in terms of the awards that he has won, some of them includes Mardi Science and Technology Exhibition, MSTE, International Engineering, Invention and Innovation Exhibition, INENBEX, Invention, Innovation and Design, IID, Malaysia Technology Expo, MTE, International Invention, Innovation and Technology Exhibition, ITEX, and many others. Of course, in addition to that, he has served in many of the associations. One of them is the Malaysian Oil Scientists and Technologists Association, and so on. Right. Without further ado, allow me to introduce our second speaker of today, technologist chemist Dr. Khalisanni bin Khalid, for his title, Flexible Nanoparticle Catalysis in the Reaction of Piperidine with Phenyl Salicylate Ions, PS negative. Right. I would now like to pass the floor to Dr. Khalisanni. You can share. Yes, we can see your slides.
Okay, many thanks, our Madam Chairman, Dr. Yvonne. Hi, you can see my slides. And first of all, I would like to thank IKM Outstanding Young Chemist Awards Committee for giving me the opportunity to do the showcase webinar. Without further ado, I would like to start my presentation slides entitled Flexible Nanoparticle Catalysis in the Reaction of Piperidine with Phenyl Salicylate Ions. So, for the research highlights, from this presentation, we understand that the values of the relative counter-ion binding constant, RXBR or KXBR, are independent of the physical-chemical characteristic of the probe molecules, which we will use in this study, namely phenyl salicylate ion PS minus, and the increase of counter-ion binding constant RXBR values leads to the changes from spherical micelles to worm-like micelles, rod-like micelles, and vesicles, which is the correlation are supported by the rheological data and microscopic evidence. For an introduction, the study for the relationship between the counter-ion binding constant, RXBR value, and the transition of micellar structure from what we call it the monomer of surfactant. We call it micelle to spherical, worm-like, and vesicle has been the interest for the scientists in these few recent decades, and our groups is focusing on the hydrophobic counter-ions. Okay, let's see the micelles and its aggregates. We have a monomer of micelles, but in the presence of a flexible nanoparticle, in the presence of the phenolates ion, flexible nanoparticle, piperidine, and the micelle will be transformed to spherical, worm-like, and vesicle. But of course, in our study, we focus on the effect of salt additives for the transformation of the micellar self-assembly. The objectives of the study is actually to determine the correlation between the relationship of a counter-ion binding constant that we studied and the micellar assembly structure, and to determine the evidence of the proposed micellar structure with respect to the relationship of counter-ion binding constant values and micellar assembly structure. And the methods that we study here is we determine the viability of phenylsilicate ion as a probe molecule. Second, we determine the catalytic effect of nanoparticle in the system in the presence of CTBr, which is surfactant, what we call it phenolate salt, water for the analysis of phenylsilicate ion. And then we study the logical properties of the nanoparticle. And then we study the nanoparticle turbidity and the analysis of nanoparticle size, and eventually we study the microscopic evidence of nanoparticle. So here I'm presenting the result for the determination of the viability of phenylsilicate ion as a probe molecule. Here we calculate the empirical constant and KXS calculated from equation 1, which has been shown below. Here we want to determine the viability of the probe molecule, which is phenylsilicate ion. And we found that the phenylsilicate ion is suitable as a probe molecule for the present study because we can see the value of RxPR in your right-hand side is actually relatively about the value of RxPR is relatively is about the same. It's around 5 to 4.54, something like that. So we will use the phenylsilicate ion as a probe molecule in the present study. And then for the determination of the effect of hyperinolysis of phenylsilicate ion for the reaction, we want to determine that the reaction will become plateau at the end of the process because we want to ensure that all the micelle have fully reacted for the reaction, and then we can see in the small plot here is actually the result that corresponded to the lowest value of salt concentration, and then this table is actually giving the value of RxPR for RxPR value, which is counter-ion binding constant for each phenolates ion, which is phenols, 2 active phenolates, 3 active phenolates, 4 active phenolates, and 2 propyl phenolates, 4 propyl, 3 isopropyl, and 4 isopropyl. And what we can see here is actually the catalytic constant Kcat increases as the concentration of the surfactant decrease. So what is actually catalytic constant, which is catalytic constant is the ability of the counter-ion salt to catalyze the rate of hyperinolysis of phenylsilicate ion in the presence of flexible nanoparticle, and each of a phenolate ion set giving different value of counter-ion binding constant and catalytic constant. So in the study of rheology, we can see here there is shear thinning and shear thickening for for each set of phenolates ion. And why we are studying the rheological properties? Because at the end of the day, we want to determine whether the worm-like or rod-like structure is present in the respective phenolate ion system. All right, this is a result and discussion for the effect of salts on the turbidity. We can see here a sodium phenolate, 2-ethyl sodium phenolate, 3-ethyl sodium phenolate, and 4-ethyl sodium phenolate doesn't give a significant reading for the effect of turbidity. However, 2-propyl sodium phenolate, 4-propyl sodium phenolate, and 3-isopropyl sodium phenolate, and also 4-isopropyl sodium phenolate contributes to the significance of turbidity. Is meant to say that actually the sample is clear, but it is gel-like structure, so that the light hardly permeates into the system. So most probably, the sample would be either in the form of vesicle or rod-like, worm-like structure. So the determination of phenolate salt sample on the particle size of flexible nanoparticle, it is found that 2-propyl sodium phenolates and 3-isopropyl sodium phenolates giving a larger particle size compared to others, which also contributes to the hypothesis that these salts contributes to the formation of the vesicle structure, micellar self-assembly. So this is the TEM result for the micellar self-assembly flexible nanoparticle. It was found that for MX, which is equal to salt, sodium phenolate, it is in the form of spherical structure. 2-ethyl sodium phenolates and 3-ethyl sodium phenolate is also in the form of spherical structure. However, 4-ethyl sodium phenolates has been found in the worm-like structure together with 4-isopropyl sodium phenolates. However, 2-propyl, 4-propyl, and 3-isopropyl sodium 2-propyl and 3-isopropyl sodium phenolate has indicated that it is in the they are in the form of vesicle structure, and MX and 4-propyl sodium phenolates are in the form of rod-like structure. And after we compared with RxBr value, which is counter ion binding constant, and neta 0, which we get from the so-called rheological analysis, it was found that the phenolates ion, 2-ethyl phenolates ion, 3-ethyl phenolates ion contributes to a spherical micelle structure, while 4-ethyl and 4-isopropyl and also 4-propyl phenolates ion contributes to the worm-like or rod-like micellar structure, while as a reference, 2,6-chlorobenzoate ion contribute to the spherical micellar structure. So, in relation to the research, we have some publication associated with respective experiment where we have published in Micron, 10 sites surfactant detergent, topics in current chemistry, bioengineered, kinetic and catalysis, Journal of Surfactant Detergent, Journal of Oleoscience, Journal of Indian Chemical Society, and so on. And what are the recommendations of the studies? So the current study emphasized the correlation of kinetic data, counter ion binding constant, and residual behavior for micellar aggregates. This research can also predict the phase transition of micellar structures. However, an intensive research is required to determine the exact transitional point of the micellar structure. The studies may require various concentration of flexible nanoparticle in the presence of salt, followed by the microscopic analysis. The present studies use the fresh flexible nanoparticle sample for the understanding of the reaction, and analytical investigation is also recommended. That the effect of time on micellar self-assembly will be studied in the future research. So we have studied the research, and and I do like to tell, I do like to inform some of the intellectual property from the from the studies. Is actually we have developed nano fertilizer using the colloid system, which has been trade secret, and also an algae-based biofilm composition patent file, and a nanovesicle for carrying a substance and a method of preparing thereof, which has been granted, newly granted. What is the potential application to the industries? Of course, the development of nanofertilizer, and also the colloidal dispersion analysis or studies in essential oil process may adapt the present study to determine the kinetic mechanism of the separation between solvent and essential oil phase. So we have done the research. What we have to do now, is it going to be in vain, or is it going to translate? What our contribution to the industry? Of course, through our research, we have successfully commercialized the outright sales agreement in relation to the production of modification of Khalisanni fertilizer, and also the outright sale agreement in relation of processing technology of the mushroom patty produced from the oyster mushroom. And this research has contributed to the two public good, which is essential oil distillation process in Mari Kuala Linggi, and also enhancing efficiency at the distillation process by using estimated virtual exhaustive technique. So these references, and I do like, and I would like to contribute special thanks for Mardi for providing the study leave scheme support and sponsoring my PhD, and also a research grant. Ministry of Malaya Bright Spark Scholarship High Impact Research for research grant and scholarship. KPG Resources, Chamber Hut for commercializing the research. Malaysian Institute of Chemistry and Malaysian Young Chemist Network, of course, Dr. Juan and friends, for commemorating the IKM Outstanding Young Chemist Award Industry 2021. And last but not least, my family, supervisors, collaborators, and fellow friends. Thank you.
Thank you very much, Dr. Khalisanni, for the talk about micelles and nanoparticles. It's very interesting how it could be very uniquely shaped, like rod legs and worm legs. I was just wondering, is there anybody who would like to unmute yourself for question and answer? That's the first thing that I would like to do.
I hope not.
All right.
But it's okay. If there's any question, I love to answer.
I do have one question from my side.
Yeah.
Right. I was just wondering, you've done a lot of research and have actually brought them to the commercialization stage. So how long does it take, or was it like, if you have an idea of doing certain research, how long does it take to get to the commercialization stage? Can you walk us through one of those scenarios or share your experience about it?
Yeah. Thank you, Dr. Yvonne, for that intrigue and a tricky question, actually. And I do believe it is a good question indeed. How long does it take? For me, when I did my PhD, I'm talking about what I'm from the industrial point of view. Yeah. So I have studied the fundamental knowledge in university, but what we have learned is actually the fundamental knowledge. There is no way the university concerned about the application, because when we are at university, our KPI is papers. There is no way papers, especially for high impact research journal. Sorry if I'm wrong. As far as I'm concerned, there is no way high impact research journal prefers applied papers. They concern very much about the fundamental knowledge and fundamental papers. So it is our responsibility to translate the fundamental knowledge to the application or applied knowledge. So how long does it take to translate the knowledge to application? For me, it's about 5 years or more. 5 years or more, because when it comes to application, they will ask you a lot of fundamental question, especially how the formation of my cells. And if you don't have the fundamental, you will fail to be an applied researcher. That's all.
I see. Great, thank you very much. Is there any other questions from the crowd? Right, can I have one last question for myself? Is there anything?
I think there's only you intrigued with me, or
No. They're probably processing.
Yeah,
Because a lot of us from like academia point of view, right? We are trained, like you've mentioned before, we're very fundamental. We're trained to like do research and then publish and things like that, that we may have like missed out on the potential to actually get our things commercialized, or it's very, I mean, it's getting more and more that we're approaching towards the innovation and like commercialization stage. But yeah, it's a different kind, I would say, a different sharing that you've given. So that's why perhaps they would like to take some time to kind of process it. But don't worry, I will actually drop Dr. Khalisanni's email along with Dr. Ng's email in the chat box later on, so that if you guys have any burning questions that you'd like to ask him, you can actually send them an email and they would be very happy to answer you.
Yeah.
I do have one question, if you would like me. So, because you're the Outstanding Young Chemist Award winner for the industry category, is there any advice that you'd like to give to potential people who are applying for this particular field? Is there any advice that you'd like to give in terms of the application process, or like how do they prepare themselves for this award?
Yeah, all right. Thank you, Dr. Yvonne. What I can say is actually the advices that I can give. Full equip yourself with fundamental knowledge, and when you are going to apply for this Outstanding Young Chemist Award industry, I do believe it's more on your contribution to the industry, how much you contribute, how much you help, how much you engage yourself to the industries. There is no more papers. Of course, papers is something that helps you to strengthen your application. But of course, what have you contributed to the industries? What have you commercialized? How you change the landscape of Malaysian industries? That's the most important things. Yeah, that's all.
Great, thank you very much once again, Dr. Khalisanni, for your presentation as well as your sharing. I would like to also thank Dr. Ng for his sharing. Now, we would like to proceed with the closing remarks as well as photography or photo session. So for those of you who have not gotten ready, please do get ready to turn on your cameras. Right, I will go on and share a screen and talk about the closing remarks, followed by the photo session. Meanwhile, everybody could get ready to turn on your cameras. Right. So, as you know, if you've followed our social media accounts, the Malaysian Young Chemist Network social media accounts, you would know that the Outstanding Young Chemist Award for the year of 2022 is now open. There are two different categories, academic and industry. So if you feel like you have what it takes to kind of apply for this, do head over. Even if you feel like you're not prepared for it yet, you can head over to get more details and prepare yourself maybe in a few years to come. Right, the application dates are as follows: 1st of April to 30th of July 2022. You can actually head over to bit.ly /IKM MYCN to get to the IKM website, giving you more details about the award as well as the application forms or nomination forms. We're calling for chemists age 45 and below, so apply now for a chance to be recognized, win a medal, as well as certificate and cash. And be able to kind of share your experience with us next year in our webinar series. Next, I'd like to say that if you are an IKM member, age 45 and below, and if you have the passion for delivering impact in the field of chemistry, come join us. We are part of Malaysian Young Chemist Network. So you can head over to Facebook, Twitter, Instagram, or just scan this to actually get to the IKM website with more details about us. Okay, so this is the end of the webinar series. I'd now like to kind of invite everybody for the photo session. For committee members, you may have already received the background. You can put them on. For those of you who don't have a background, don't worry, just turn on your cameras and get ready. We'll be taking some photos shortly once everybody's ready. Give me a second. Full screen. Right. Everybody look at the camera. Get ready. In a count of 3, 2, 1, smile. Right, I'm gonna take a few. In a count of 3, 2, 1, smile. One more. In a count of 3, 2, 1, smile. Great. I would like to also invite Dr. Pang to say a few words. Dr. Pang, the floor is yours.
Okay. So thank you, Dr. Yvonne, to help us to coordinate for today's webinar. Dr. Yvonne, can you hear me?
Yes,
Can,
we can hear
okay.
you.
So I would like to thanks two winners to Dr. Ng and also Mr. Khalisanni.
Dr. Khalisanni.
To join us to give us the to give a talk to us and also for this last year Young Chemist Award and also this year Young Chemist Award. I think the successful of this award is due to our outstanding Young Chemist Award, our committee member. I want to thank Dr. Yvonne, our committee member, Dr. Yvonne, Dr. Neil, and Dr. Juan, and also Dr. Tan Yi Sing and Dr. Ellie from Sunway, and also another Dr. Neil from Nottingham to help us along all this process to make this outstanding Young Chemist Award to be success. Okay, so today also many of the participants is my ex-student and my current student from the TASI, UITM, and also UKM. I want to thanks all to join us for this meeting, and also some of the friend is come from my ex classmate from the UKM and also UM. So I want to take this opportunity to thanks all of you to join us for today's webinar. Thank you for your support. Okay. So that's all.
Great. Thank you very much, Dr. Pang. And thank you to all who are in attendance today. It has been a pleasure. Thank you to both speakers. And yeah, we'll see you next year for something similar. We'll look forward to the crowning or the announcement of the next year's Outstanding Young Chemist Award during Malam Kimia of this year. Bye. Take care. Stay safe, everybody. Thank
Bye-bye.
you.
Thank you. Thanks.
Bye-bye.
Bye.